Why did I even hit start if my camera's blurry? I feel like this was a poor execution of a video, but I'm not gonna restart it because this just seems funny. While you guys are waiting for me to focus my camera, we're in advanced math lesson 88, exponential functions, growth and decay. This should be the second video. Yeah, well, you know what? This is the second lesson that we typically skip during our trigonometry year. Because there's not a whole lot that we can expound on, and it's not the main focus of that year. But hey, it's a great lesson for pre-calculus. So if you're in the trigonometry class and I'm having you do this lesson, it's either because we got ahead or I forgot. And if you're in the pre-calculus class, then just ignore everything I just said. So exponential functions of growth and decay. So the function here is this equation. And this equation has to be memorized. Why is my camera doing that thing again? I feel like I'm going to have to buy a new... Anyways, let's get back to business. Okay, so this is our equation for exponential growth or decay. It's a sub t equals a sub 0 times e to the power of kt. We need some context because this is just a bunch of letters, all right? I remember when I was in high school, I saw AOE, and I always thought Age of Empires, which was a video game back in the 90s. Never mind, let's not talk about that. We're getting off track. Let's talk about the A's, all right? So the A stands for amount, all right? Now, we have amount at 0 and amount at t. T is time, all right? So A of t is amount at a specific time. A sub 0 is the amount at time of 0, or, the amount at 0 before the growth or anything began, right? So it's starting from nothing, okay? E is our universal rate of change, think Leonard Euler. K, just like in our scale factor, is our mathematical constant. So K is going to be the constant for the growth or rate of change. And then T, once again, is still time. So this is cool. Once we understand all these, then we can understand exponential growth or decay. Now, the key to understanding whether or not you're having exponential growth is your K. If your K is a positive number, then you're having exponential growth. If your K is a negative number, you're having exponential decay. Pretty simple, right? Yeah, decay. All right, let's get to an actual problem here instead of me telling terrible dad jokes. Okay, so they tell us the number of... Oh, yeah, also these exponential growth problems are really good for sciencey things like bacterial growth. They're good for studying exponential growth in finances and stuff like that. It's really good thing, and it's a good use of the letter E. Anyways, our problem. The number of bacteria present at noon was 400, and 9 hours later, the bacteria numbered 800. Assume exponential growth and find the number of bacteria present at noon the next day. So, bacteria present at noon, 400, 9 hours later, 800. So what we're going to do here is we're going to plug in these values into our equation and attempt to solve for K, or a constant. So, the amount at the time of 9 hours later is 800, all right? So we can plug in this equation. We can have 800 at the amount at 9 hours later. Oh man, that hurts. Okay. Don't know if you noticed this Band-Aid on my finger, but I smashed my finger in the window the other day, so now I have to write kind of funny. It's starting to get better, but not totally. Maybe I'll just try to write without my index finger. That might work. Okay. Where was I? Yeah, so the amount of time at 9 hours later is 800. The amount at 0 is 400, right? Because that's going to be noon, our starting point. Then we're going to multiply that times E, and then K, our constant, times the time, which is 9 hours, right? Now, what we have to do here is we have to solve for K. The way we're going to do this is we're going to use our logarithmic rules, which I believe that's one of the lessons that we reviewed at the beginning of this school year. We should have started around like 80 or 81. And yeah, I think we started at 81. And we're going to be using a natural log of each side to solve for the unknown in the exponent, right? So that's why we did all that, so we can learn how to solve these exponential growth equations. So I'll go ahead and I'll take the natural log of 800. And then I'll take the natural log of 400 times e to the power of k9. So from here, we're going to go ahead and take our calculator, and I'm going to start using the TI-83 here, because I know a lot of you have TI-83s, TI-84s, TI-83s or TI-89s, and they're a little bit you know, the TI-84 I have is a little bit farther away from the type of calculator you're using. Still close enough, but this one's probably similar to what most of you have. Also, the other advantage of the TI-83 is it's not an LCD screen. It is an LED. No, sorry, not LED. I don't know. It's got a different kind of screen. This screen gets glares. This one, not so much. I mean, it glares a little bit, but it's more monochrome. So, yeah, I should probably clean this up. Mr. Gamble gave this to me last year for use in the classroom, and I never really cleaned it. So, apparently it belonged to his sister. Anyways, now that we're done wasting about 60 seconds on something that has nothing to do with your lesson, let's go ahead and finish solving for k. So I'm going to take the ln of 800, or the natural log of 800, and I get 6.68. Again, for those of you who need the refresher, we simply just press ln 800, enter. That gives us our answer. So that's going to be 6.68, and again, I like rounding to the hundredths place. I'm going to write with not my index finger. 6.68. All right, and then the ln of 400e. So the funny thing here is this is a multiplication. So this can actually be written as the sum of logarithms. So this one is going to break into the ln of 400 plus the ln of e to the power of k9. So what that does for us is this one is going to cancel out, and then it's just going to become 9k. Right, so we have 9k instead of k9 because it sounds too much like, you know, a dog. And then we'll simplify the ln of 400 by punching it into our calculator, and we get 5.99. So then we have 5.99 plus 9k. From here, it's just simple algebra. We're going to subtract 599 from each side. Having a tough arithmetic morning here. That's going to be 9, 5, and then 6. So 0.69 is going to equal 9k. From there, we just divide by 9. I'm going to go ahead and use my calculator because, like I said, I'm having a rough morning as far as thinking, probably because my finger hurts. And I get 0.76666, which I'm going to round to 0.77. All right. Now, remember, my k, or my constant, is equal to 0.77. I am not done with the problem, because if we go back to the original problem, which I know was like a whole 4 minutes ago, they want us to find the number of bacteria present at noon the next day. So noon the next day is how many hours later? 24 hours later. So if we're starting at noon, 24 hours later is going to be noon the next day. So now we have a brand new problem. We know the constant, but we do not know our ending time. So our amount at time is going to be unknown, or it's going to be amount at 24. We do not know that. Our amount at 0 is still going to be 400 because that's the starting point. E is still E because it's constant. Our K, which we now know, is 0.77. I'm putting that in parentheses. And then our time is 24. So in order to solve this, we just have to simplify the right-hand side of the equation now. And then we will know how much bacteria there was 24 hours later. So let's go to our calculator. We'll go ahead and take 0.77, multiply that by 24. So that gives me an exponent of 18.48. So now we have 400 times e to the power of 18.48. And I can do that very simply on my calculator. I don't have to do any logarithmic rules. I'll just take e to the power of 18.48 and parentheses. I get that. That is a big number. And I'm going to take that big number. I'm going to multiply it by 400. And I get an even bigger number. Wait, how'd that get smaller? Wait, I had that. I multiplied it by 400. Now I'm at 4.2. Oh, times e to the power of 10. Okay, very good. With the exponent to the power of 10. Okay, so, wait, how did they put their final answer? Is it in scientific notation? Nope, I think I made a mistake. Hold on. Yeah, I found my mistake. Okay, if we go up here, we look at my calculator, I have 0.076, and then I used 0.77. All right, so this could have been a short video, but I made a mistake. So let's go back up here, and we'll change that. Let's go in red, so that way we can show the error here. So this one is 0.077 times 24. So that changes everything a lot. I was like, that number is huge. I think it's a little too big. And it was. So let's take 0.077. We'll multiply that by 24 for the exponent. That gives us 1.848. All right, so that's a little bit different than 18.848. So 1.848, we'll take second e to the exponent of 1.848. That seems much more reasonable. We have 6.347. I'll take that, multiply it by 400. And I get 2,538.85. I'll round it to 2,538.85. And is that's good enough. All right. So the book gave the answer of 2,539 bacteria. I'm okay with 0.85 because that would round up to 2,539. I think it's really strange they got a whole number. I'm not sure if they rounded that. But again, just like with any of the problems, if you're within a few hundredths of a number, we're okay. That's it for this lesson. Hey, I was trying to make one finally under 10 minutes. Didn't get there, but I think we did pretty good. If you have any questions, let me know on the school website, and I'll see you in class.